A linked list stores data where each piece points to the next in a chain. Unlike arrays, linked lists store items separately, connecting them with links. This allows linked lists to grow and shrink easily without reorganizing data. Think of a linked list like a train, where each car holds data and connects to the next. The train can get longer or shorter by adding or removing cars without disturbing the rest. Why linked lists exist? Data often changes size in programs. Items may need to be added, removed, or moved. With arrays, changing size can be costly. If an array fills, moving everything to a new memory location takes time and slows the program. A linked list avoids this. Each data piece is stored separately and linked. Adding or removing is easy. Just attach or detach a link. No rearranging is needed. Linked lists are useful when the number of elements constantly changes. How a linked list works. A linked list consists of nodes. Each node has two parts: data, the value, and a pointer, indicating the next node's location. The pointer chains nodes together. The list starts at the head. From the head, you follow the chain. Nodes don't need to be next to each other in memory. The pointer tells you where to go next. A real-life analogy. Imagine a scavenger hunt. Each clue has a message and the next clue's location. Clues aren't in one place, but you follow the chain as each points to the next. Linked lists work similarly. Follow pointers to reach desired data. Key characteristics of linked lists. Dynamic size. The list can grow and shrink easily. Efficient insertions and deletions. You just change a few links. Slow for finding items. You must start from the head and follow nodes one by one. Flexible memory usage. Nodes do not need to be stored together in memory. Linked lists trade search speed for modification speed. Comparing linked lists and arrays. Arrays, continuous memory, fast direct access, costly growing/shrinking, best for fixed-size collections. Linked lists, scattered memory, slower sequential access, easy growing/shrinking, best for changing size collections. For fixed data with rare changes, arrays are simpler and faster. But for constant insertions or deletions, linked lists are better. Different types of linked lists. Singly linked list. Each node points only to the next, the simplest form. Doubly linked list. Each node points to both next and previous, allowing bidirectional movement. Circular linked list. The last node points back to the first, forming a loop, useful for continuous rotation. Where linked lists are used. Linked lists are used where data changes frequently. Music and video playlists. Playlists can grow, shrink, or reorder without rewriting. Undo/redo systems. Each action links to the next and previous action. Operating systems. The system scheduler uses linked lists to manage running tasks. Navigation systems. Linked structures represent dynamic routes or paths. Memory management. Compilers and OS memory managers use linked lists to track available memory blocks. Advantages of linked lists. They grow and shrink naturally, with no need to move existing data. Efficient for inserting and deleting items in the middle with flexible memory allocation. Limitations. Searching is slower as you must start from the head and follow links. They take more memory due to pointers and are not ideal for fast random access. Final summary. A linked list is a data structure where each node contains data and a pointer to the next item. Unlike arrays, linked lists scatter items in memory, connecting them via links. This makes them excellent for frequent data size changes, like adding or removing items. However, sequential access makes searching in linked lists slower than in arrays. A linked list is a flexible data chain, great for frequent changes, but slower for quick lookups.